Ever wondered what happens when titration steps out of its aqueous comfort zone? Well, that's where the captivating concept of non-aqueous acid-base titration comes into play. This isn't your everyday titration, folks. We're going beyond the bounds of water here. Non-aqueous acid-base titration is a unique process where we quantitatively analyze a specific substance by reacting it with a known amount of base or acid. But here's the twist. All this happens in a medium that is not water. Quite a departure from the norm, isn't it? This technique opens up a whole new range of possibilities, allowing us to study compounds that are insoluble or unstable in water, and giving us valuable insight into their intriguing chemical properties. But that's just the tip of the iceberg. So, let's dive deep into the fascinating world of non-aqueous acid-base titration. Navigate through the realm of solvents where some dissociate and others don't. Welcome to the fascinating world of chemistry, where we'll be exploring the difference between dissociating and non-dissociating solvents. Let's start by understanding what a solvent is. A solvent is a substance, usually a liquid, that other substances can dissolve into. Solvents play a crucial role in non-aqueous acid-base titration, a method used in chemistry to determine the concentration of an unknown acid or base. Now, what distinguishes a dissociating solvent from a non-dissociating one? It's all in the name. Dissociating solvents are those that break down into ions when they dissolve in a solution. This is a process called ionization. These ions can carry an electric charge, which can be of great utility in the titration process. For instance, water is a common dissociating solvent that ionizes into hydrogen and hydroxide ions. On the other hand, non-dissociating solvents, as you might have guessed, do not ionize when they dissolve. They remain intact, meaning they retain their molecular structure. An example of a non-dissociating solvent is oil. Why does this matter? Well, the choice of solvent can significantly impact the titration process. Dissociating solvents can help increase the conductivity of a solution, making it easier to determine the endpoint of a titration. Non-dissociating solvents, while they might not aid in conductivity, can be useful in other ways. For instance, they can help dissolve nonpolar substances that dissociating solvents cannot. So, the next time you're about to carry out a titration, remember to choose your solvent wisely. It can greatly influence the accuracy and efficiency of your experiment. Remember, the choice of solvent can make or break your titration process. Stay tuned as we delve deeper into the intricacies of non-aqueous acid-base titration in the upcoming scenes. Unravel the secrets of acid-base character and their leveling and differentiating effects. In the fascinating world of non-aqueous acid-base titration, solvents are not mere bystanders. They actively influence the acid or base character of the substance under scrutiny. Different solvents can either amplify or diminish the acid-base properties, leading to intriguing outcomes. Let's delve into the leveling effect. Picture this. You have a group of strong acids or bases. In water, their personalities stand out, showcasing their true strength. However, when these strong acids or bases are introduced into certain solvents, a peculiar phenomenon occurs. Their distinct characteristics level out, making them behave similarly. This is what we call the leveling effect. It's like a school uniform policy, where all students, regardless of their unique personal styles, are made to look alike. On the flip side, we have the differentiating effect. Think of this as the talent show, where everyone gets to flaunt their unique abilities. In this case, weak acids or bases, when placed in certain solvents, display distinct behaviors. The solvents allow these weak acids or bases to express their individuality, highlighting their differences. This is the differentiating effect. Now, why do these effects occur? It's all about the solvent's ability to donate or accept protons. In the leveling effect, the solvent's proton donating or accepting abilities overshadow the strong acids or bases, causing them to behave in a similar fashion. Conversely, in the differentiating effect, the solvent's limited proton donating or accepting abilities allow the weak acids or bases to show off their unique characteristics. In essence, acid-base titration is like a dance. The acid or base is the dancer, and the solvent is the dance floor. The type of dance floor can either make all dancers appear the same, or allow each dancer to showcase their unique moves. In the world of titration, it's It's all about finding the right balance. Uncover the roles of solvents, titrants, and indicators in non-aqueous acid-base titration. These components are the unsung heroes of the titration process, each playing a unique and vital role. Let's begin with the solvents. Solvents are the medium in which the entire titration process takes place. They provide the environment necessary for the acid and base to interact. In non-aqueous titrations, we use solvents other than water, like acetic acid or methanol, which can enhance the reactivity of certain substances and enable the titration of weak acids and bases. Moving on to titrants. They are the known substances that we use to determine the unknown concentration of the analyte, or the substance being tested. Titrants are carefully chosen based on their ability to react completely and specifically with the analyte. For instance, perchloric acid in acetic acid is a popular titrant used in non-aqueous titrations. Lastly, we have indicators. Think of them as the conductors of this symphony, providing cues for when the performance, or in this case, the titration, is complete. Indicators change color at the end point of the titration, signaling that the correct amount of the titrant has been added. In non-aqueous titrations, we often use colored substances like crystal violet, which changes color in response to changes in pH. Each of these components, the solvent, the titrant, and the indicator, has a pivotal role to play. The solvent sets the stage, the titrant performs the main act, and the indicator signals the finale. Together, they ensure the titration process is accurate and effective, allowing us to determine the concentration of unknown substances with precision. So, the next time you think about titration, remember this intricate dance of chemistry. It's not just about adding one substance to another. It's about choosing the right players, setting the right conditions, and observing the subtle signals that tell us we've achieved our goal. Like a well-rehearsed symphony, each component plays its part in the titration process. Discover how non-aqueous acid-base titration helps in the determination of acids and bases. This fascinating branch of analytical chemistry allows us to determine the concentration of an unknown acid or base by reacting it with a known quantity of the other. Let's delve into the process. We start with a solution of unknown concentration, either an acid or a base. To this, we gradually add a solution of known concentration, the titrant, until we reach the endpoint of the titration. This endpoint is the point where stoichiometrically equivalent amounts of acid and base have reacted. But how do we know when we've hit this magical point? This is where our colorful friends, the indicators, come into play. Indicators are substances that change color at or near the endpoint of a titration. They serve as our visual cue, letting us know that our reaction is complete. A well-chosen indicator will undergo a clear and distinct color change right at the endpoint, making it easy to spot. For instance, phenolphthalein, a commonly used indicator, changes from colorless to pink as we transition from acidic to basic conditions. In non-aqueous titrations, choosing the right indicator can be a bit of a challenge, as the pH range over which the color change occurs can be different than in water. However, with a bit of trial and error, or a handy table of indicator color changes in different solvents, we can usually find an indicator that fits the bill. The beauty of titration lies in its simplicity and precision. Every drop of titrant we add brings us one step closer to the endpoint. Each drop can make a difference, shifting the balance of the reaction and inching us closer to our goal. In the grand scheme of titration, every drop counts. The precise control, the anticipation of the color change, the satisfaction of knowing you've determined the concentration of an unknown. It's a process that's as beautiful as it is useful. So, whether you're a seasoned chemist or a curious beginner, there's something in titration for everyone. Journeyed through the world of non-aqueous acid-base titration we've delved into the complex mechanisms that underpin the field, from the critical role of dissociating and non-dissociating solvents to the subtle nuances of acid-base character. We've explored the fascinating concepts of leveling and differentiating effects, and how they shape the behavior of acids and bases in different environments. We've also unraveled the mysteries of solvents, titrants, and indicators, and their pivotal roles in the titration process. And finally, we've seen how all these elements come together in the determination of acids and bases, a process that is as much an art as it is a science. So the next time you see a titration process, remember there's more to it than meets the eye. This is just the tip of the iceberg. There's a whole universe out there waiting to be discovered. Subscribe for more, because you won't find me later.